Hello, my name is Michael West Jr., and I'm a graduate student at MIT in the Department of Mechanical Engineering. Today, I'll be presenting our recently published paper titled Dynamic Primitives Limit Human Force Regulation During Motion. Humans excel at physical interaction despite long feedback delays, slow communication, and low bandwidth actuators. Yet, little is known about how humans manage physical interaction. A quantitative understanding of how they do is critical for designing machines that can safely and effectively interact with humans. This understanding should be in the form of a simple mathematical model that not only describes humans' capabilities, but also their limitations. In robotics, hybrid control allows simultaneous, independent control of both force and motion, and it is often assumed that humans can modulate force independent of motion as well. This work experimentally tested the hypothesis that humans could regulate force independent of motion. We refer to independent control of force and motion as direct force control. As shown in direct force control, applied force is directly related to the applied force. Thus, errors in contact force will be independent of motion. Alternatively, if errors in contact force are dependent on motion, we propose the shown indirect force control method, where force is coupled to motion via the highlighted impedance term. So how do we experimentally test these opposing controllers? A subject sat in front of a robotic manipulator that moved in the transverse plane about an elliptical trajectory that followed the 2/3 power law. They are specifically asked to apply a 5 Newton force on the robot's handle in its tangential direction of motion. The experiment was split into 5 blocks, each consisting of 15 trials, where each trial consists of 4 cycles around the ellipse, meaning in total, subjects traversed the ellipse 300 times. Furthermore, the blocks alternated between given visual feedback, not given visual feedback, and so forth. Where the visual feedback is as shown, where subjects sat in front of a black screen that showed a static white bar, which represented the target force, and a moving red bar, which represented their actual applied force. Lastly, we obtained data from another similar experiment where subjects were asked to apply 0 newtons of force in a single block of 10 trials with no visual feedback. Here we show the root mean square force error in both the 5 Newton and 0 Newton experiment as a function of trial. To assess performance improvements, we fit a linear model to each block as shown by the red lines. And then we found where there was a significant slope. As shown by the red asterisk, this only occurred in the first block where subjects were initially given visual feedback. Thus, we conclude that there was limited improvement in force error over practice. Upon further inspection, it was found that force error is motion dependent and periodic. This can be clearly seen in the representative subject graph shown on the left. To quantify this periodicity, we computed the autocorrelation function of each subject's force signal and found where the lag of maximum autocorrelation occurred. As seen in the graph in the middle, these peaks occur very regularly at 180 and 360 degrees. This observation was robust across all subjects in both experiments, independent of feedback condition and practice. The periodic force error seen here suggests the controller appears to be content with good enough performance, which can be obtained using a limited set of primitive oscillations and a sufficiently low mechanical impedance. This is consistent with the theory of dynamic motor primitives. To conclude, despite extensive practice with and without visual feedback, subjects could not accurately apply constant force during motion. In fact, subjects' force errors were motion dependent, which suggests a coupling between motion and force, which is described in the indirect force controller via the impedance term. Moreover, the observed periodic pattern of motion-dependent force is consistent with planned motion composed of oscillatory primitives. These findings suggest that a simple mathematical model combining dynamic motion primitives with mechanical impedance as an additional primitive is competent to describe how humans control physical interaction. This work is of particular concern in human quantification of performance and estimation of human intent. Thank you for listening to my presentation, and please do not hesitate to contact me if you have any further questions.